All right. Okay. Come on. Oh man. There we go. Oh, there we go. All right. It's always very slow to respond to me on that. The guys in the room don't see this, but I have to fight with to duplicate the display. All right. So we've been talking about Fourier series, right? And we've basically been learning about the different forms of the series. So there's really two relevant sections in the textbook for us right now for this unit of the class. 9.1, which is basically what are the three forms of the Fourier series. As I've said, there's a lot of equations there. If you looked at that, there's a lot of equations, okay? Today, we're gonna finish the example that we started on Tuesday, and we're going to try to simplify a little bit of this, all right? To see how we can answer some of the questions like Zach asked there about how we relate the theta to the A and the B and all that sort of stuff. All right, then there's this question about how do you get the coefficients when you have a signal that you don't have the equation for that already has cosines and sines, right? The stuff that you've got on the homework is in a way, even if you're struggling with it, is straightforward because you were given an equation, all right? In reality, you don't typically work that way. You're given data, right? You're given some, like I did the thing with my voice. I'm given, you know, my phone has the microphone, it records my voice, and it's basically doing analysis on it. So the question is, how do you do that analysis? So we're going to get into that a little bit today, but we're going to wrap up with what we've been talking about the last two times. All right. So I've said this before, and I'm going to say it again one time real quick, right? If I have a circuit, and again, I think of most things in terms of circuits because that's where this is useful, or one of the places at least where this is useful. If I have a circuit like this RC circuit that I've got here, and I put a cosine voltage into it, okay? The voltage across that capacitor is also going to be what? What's the voltage across the capacitor look like if I have a cosine voltage going into the circuit?
Sinusoidal?
Yeah, it's going to be sinusoidal, right? And it's going to be shifted, you know, a little bit to the left or to the right, depending on the values in the circuit. All right, now, because of this, right, again, the right way to do everything is to write out a differential equation for the circuit. That differential equation has two solutions. One is the steady state solution. The steady state solution is the cosine piece. It also has a transient solution, which represents sort of this memory effect of this thing. But again, what we always said is, usually most of the time, we don't care about the transient. Most of the time we don't, right? It's one of those things where we don't care about it until we do care about it, okay? So in other words, when the transient matters is usually because we have a problem in our system, all right? And for the most part, like in 2112, you're spending a lot of time talking about impedance. And you do that because most of the time you really just care about what's happening in steady state. Okay, so if I did impedance analysis assumes what? And I've said this probably at the beginning of the last two lectures, but what's the implicit assumption every time we do impedance analysis?
An AC source.
Not an AC source. Well, you're ignoring the transient. So in other words, you're only considering steady states. That's part of it, right? And Zach, I heard you say AC source. AC source is almost right. Not an AC source, but a what? More specifically, sinusoidal.
Periodic.
Sinusoidal source, okay? So good comments there about AC and periodic. AC basically means that I have something that is alternating. So that square wave is AC and periodic, okay? I'd call that an AC waveform because it's alternating. And I'd call that periodic because it fits our definition of periodic. Really, anything that's periodic fits my definition of an AC waveform. All right. More specifically, what I have to have is a sinusoid. If I don't have a sinusoid, impedance doesn't work. All right, so if I have a square wave like I have here, that square wave is periodic, and we've talked about this plenty of times now, but the definition of periodic is right there. If I go a period ahead from where I am right now, the waveform better have the same value. If I go a period behind, the same thing must also be true, right? That's the definition of a periodic waveform. Now, that guy, that square wave, which is again a pretty common waveform in circuits, right? Particularly in digital circuits, we have that all the time, right? That particular waveform right there is an AC waveform. It is periodic. Impedance analysis does not work, right? In other words, if I looked at this thing and said, well, the period is T, so omega is 2 pi over T. And I said, well, this guy has an impedance of 1 over j omega C. And this guy has an impedance of R. I couldn't say that V out is equal to the amplitude of V in divided by my voltage divider relationship here. All right. That does not work. All right. That only works if I have an AC waveform. Or sorry, if I have a sinusoidal waveform. Only works if I have a sinusoidal waveform. Okay. And so I got to be careful about that. Right. And that's the reason one of the reasons we talk about Fourier series is we say, well, actually turns out that that square wave isn't just a square wave. It's actually a sum of sinusoids. Okay. And that means I can do that impedance analysis at each of those frequencies inside that square wave, right? Each of the sine waves that comprise it. All right. We'll deal with that in the next portion of the class, right? When we talk about things like filters and how we design sort of filtering systems and the math behind that. Okay. We'll talk about that later. The important thing is that this tool of Fourier series is useful to us because very often we have periodic functions that I want to use things like impedance analysis, or I want to look at that thing and I want to be able to figure out what sinusoids are in it. That's usually useful to me in some way. And we'll see some applications of that as we go. Right. But what we said is any periodic waveform can be expressed as a linear combination of periodic basis functions. All right. And so what I defined last time is I said, what does a linear combination mean? What does it mean to be a linear combination? All right, a sum of a scaled multiple of these things, right? So in other words, I can take some amount of sine and some amount of cosine and some amount of cosine omega t plus phi, right? So there's basically three options that I have for Fourier series. I can represent in terms of a combination of sine and cosine as a combination of cosine omega t plus phi, or a combination of e to the j omega t and e to the minus j omega t. All right, the thing to remember, this last one here, e to the j omega t, I keep using that one a lot, the complex form of the series. What does e to the j omega t look like? What is that? I mean, it's not a cosine wave. It's, well, okay, so Philip's in the room making a circle, right? So basically what it is e to the j omega t, if it's here, right? It's a vector, right? So this is a real and imaginary part. This is e to the j omega t. Where would e to the negative j omega t be?
Below it.
Be where?
Just opposite to it.
Just opposite underneath it.
Yeah, it'd be down here, right? E to the negative j omega t, right? Now, the question is, as time advances, these vectors move. We talked about this idea of a dynamic phasor at the beginning of the semester, right? E to the j omega t, as time advances, which way does he move?
Counterclockwise.
Counterclockwise, right? So he moves counterclockwise. How about his compadre down here?
Clockwise.
Clockwise. All right, so one's moving in the positive direction, one's moving in the negative direction. The sum of those two things always looks like what?
0.
Not 0 per se. So if I take two vectors like that, just think of them as vectors. Don't think about any imaginariness to it. What is the sum of two vectors like that? One with an angle positive and one with the same angle negative. What would that sum look like? right? Their x components are gonna, in other words, their x direction components, their imaginary components are gonna cancel, right? So it's gonna be all x direction, and it's gonna be how big? Yeah, well, how big is the sum gonna look like if I sum those two vectors? Where's the sum gonna be for those two vectors? E to the j omega t plus e to the minus j omega t. So if one's up, one's down, where's the sum gonna be, and how big is it gonna be?
Gonna be along the x-axis.
Along the x-axis, and how big?
As big as, well,
It's going to be twice as big. It's going to be twice as big, right? And I know it's going to be twice as big because I'm adding the x component, which means the real component of the top vector and the bottom vector. So I'm going to get basically twice, right? That led us to this idea that cosine of omega t is always equal to 1/2 of e to the j omega t plus 1/2 e to the minus j omega t. Two rotating vectors, one rotating forward, one rotating backward, all right, that sum up, and they're going to give me twice the size of cosine. Because remember, the real part is always a cosine term, right? I'm always going to get a real part if I sum those two vectors together, right? And we looked at that, we looked at a picture of that previously. I just wanted to remind us of that. So way back when, all right, I got lots of stuff here. All right, but I'm going to run this here real quick. All right. So what I've got here, if you look at the top image here, what I see is those two vectors rotating, and then I see the sum of them. And then at the bottom, I'm plotting the real part and the imaginary part of the sum. All right. So if you watch what's going on, the sum basically traces out cosine as time advances. So I'm playing this very slowly, but I'm basically playing what happens when this guy runs. All right, so here it goes. So we'll do it again. So there's the two vectors rotating, and there's the sum. So the sum is always twice as big, right? The sum here, what I'm doing is plotting the sum here in time on the bottom, right? It's completely real, right? It never has an imaginary part to it.
And
right.
So do the imaginary parts, that bottom plot, is that just saying the imaginary parts go away once it's plotted?
Yeah, the imaginary parts are zero. So basically what I'm doing is you can see this big vector here. That's the sum of them at any given point, right? So what I'm doing is what I'm plotting at the bottom is I'm plotting the real part of the sum and the imaginary part of the sum. So at any given point in time, the imaginary part of the sum is always zero, right? Which is what it should be, because what we said is Euler's identity says that e to the j omega t, right? Euler's identity says this right here: cosine omega t equals 1/2 e to the j omega t plus 1/2 e to the minus j omega t. So it better be just cosine, and it better be entirely real. There's nothing imaginary about that. I'm taking two vectors that are complex, but their sum is entirely real. All right, which means that it can be e to the j omega t plus e to the minus j omega t is a model for something that happens in the real world, even though it doesn't really happen in the real world. It's a model for what happens in the real world that is easier for me to manipulate mathematically, and is also, a little bit more compact for me to sometimes deal with in code. Okay. Does that answer your question, Nate? Sort of? Kind of?
Yeah, no, that answered my question. Thanks.
Okay. All right. So basically, we're going to go back to the forms of the series here in a little bit, but that's our basic issue. Daniel. All right. Uh-oh. Hopefully I don't crash my computer. What did I do? There we go. Okay. All right. All right. So we're gonna look at those forms of the series again, right? But we basically say we've got these three different ways of thinking about any kind of periodic waveform. So I gave this example before. This is a scaled down version of the voltage at the wall here in EPIC, right? And it is, you can tell that it's periodic. It looks like it's repeating. And if I looked at it, you'd see it's repeating it at 60 hertz is the fundamental frequency of it that it repeats at, which means it's got a period of about 16.67 milliseconds. All right. And if you look at it, it is clearly not sinusoidal, but it is AC, it is periodic, right? The question that you typically ask is, I don't know what the equation for this is, right? This is basically, I just stuck something in the wall with a sensor and we measured it on an oscilloscope and that's what I saw. I don't know the equation for that. I want to know the equation for that, because if I know the equation for that, then I can do some design with that, right? But the real problem that exists in the real world typically is you're given data, and from data, you got to go to an equation, all right? Not the way that we typically do problems, right? And we typically, like even, most of the time when you guys are doing problems, right, you're given an equation and then you're trying to figure out what the waveform is. Well, that's not the way the real world works. It works in the reverse way. All right, we're going to learn a little bit more how to approach that here at the end of class today. All right, so in other words, I'd want to look at something like this waveform or that waveform here and effectively determine things like, well, at each of the different harmonics, what is the amplitude there? Right? What is the amplitude of the cosine and sine wave that's there at those particular harmonics? All right, so we'll talk more about how we do that here today. So let's go back to our basics and just remember this. So we talked about this thing. If I have a square wave, that's a common signal, has a period t, has a frequency 1 over t, and has an angular frequency of 2 pi over t. Now I should be more careful. A lot of times I use frequency interchangeably, right? But angular frequency is omega, right? Angular frequency is omega because that is in radians per second. It's how fast does the angle change. All right, but again, engineers typically refer to things in hertz, which is F, okay? All right, don't ever say something is 377 radians per second if you work at Duke, right? That's not how an engineer thinks. All right, but that is how sine is defined. Now, what we said is those are our key things, right? We defined what we called a fundamental frequency, and the fundamental frequency we said was the smallest frequency in that waveform. The largest period, the smallest frequency. All right. And, we talked about this before. Basically I can sum up sine and cosine and get them to create a waveform, right? So the example I gave was for the square wave. I could keep adding in this case, keep adding in sine waves, and eventually it kind of adds up to the square wave. Okay. Question is, how do we figure out what those unknown amplitudes are there? In that example, B1, B3, B5, B7, how do I figure out all that stuff, right? That's our goal, right? Because if we can do that, then we can represent that square wave voltage source now as a sum of a bunch of voltage sources, right? Which ultimately is going to make our life easier as designers. Okay, so 3 forms of the series. All right, I got the sine cosine version, which is probably the one that's most commonly used in math. All right, if you take a math course, typically you're going to see the sine cosine version. Engineers tend to use the complex version. All right, and there is also the shifted cosine version. Now, the shifted cosine version, I say, is sometimes the most natural, because if I think about what happens in a circuit, is if I put cosine in as the voltage source, there's a shift that happens at the output. All right, there's a shift in voltages and currents from the cosine, all right, that I applied at the input. So in some ways, that's the most natural. And what we want to be able to do is in all the problems you have in homework 6, you see, when you look at the equations that I gave you, you see the waveform in a particular form, one of these 3 forms. And your job is to basically shift and sort between the 3 forms. All right, and it's really just meant to get us comfortable with the basic concepts. So we're gonna pick up with the example that we we started on last time, and I didn't get as far as I wanted to, but I want to go through that example a little bit more today to help you out with homework 6. All right. Now, our core definitions, we said the fundamental period or frequency. So the largest period of the waveform, the smallest frequency, and the harmonic number is n, right? So basically what you see here, we're going to talk about this summation notation here. But this summation notation basically means I keep adding cosine and sine at different frequencies. And I say that the frequencies are harmonically related, which means that they're evenly spaced. They're integer multiples of each other, right? So what I said then is if I have a fundamental of 10 hertz, then the second harmonic is 20 hertz, okay? The third harmonic is 30 hertz, okay? What about the frequency of 0 hertz? What do we call 0 hertz? We call that DC. All right. So I could call that, if I wanted to, the 0 harmonic. All right, I could call it that. All right. That DC value, another way to call that is we can call that the average value of the waveform. All right, we're going to treat it specially. All right, we're going to talk more about that today as we go. This guy here, the terms that we'll use for it, we'll call it one of two things. Oftentimes, we'll call it the fundamental, but I can also call it the first harmonic. All right, the first of those waveforms that are there. Okay. All right. So last time we were looking at this example. This guy was periodic. Okay. So I've got a graph of this thing. All right. It's an ugly looking graph. All right. But I can see that this guy is clearly periodic. And we talked about this last time. I see the period there, right? I can see that it looks like this guy reaches a peak value of about 80, right? And then as I skip ahead a certain amount of time, capital T, it's about 80 again. All right. So he's clearly periodic, and you can see the periodicity to it. All right. Now, if I look at this here, the equation that I'm given is this guy. S of T is that. All right. Now, this is very similar to the types of problems that you have in homework 2. All right. In this, or not homework 2, problem 2 of homework 6. Okay, it's very similar to what you have there. Now, what I talked about last time, I'm going to write it out a little bit more explicitly, is for all those problems, you've got a pretty explicit process to kind of go through and to follow. Which the first part here is you want to find the fundamental period or the fundamental frequency, right? Find either one, right? You find one, you know the other. The next step is to determine which harmonics are actually present in the waveform, okay? The third step is basically figuring out what the coefficients are, all right? And the way that you do that, you know, is what I say here. You use the most natural form, just from inspection, okay? When I look at that, you see the most natural form, and then I try to convert between the different forms. Okay, so for what I've given you here, all right, S of T equals 10 plus all that stuff. Which form looks the most natural in this case to start with? The sine cosine form, all right? Because this guy is in sine cosine form. If I had a bunch of stuff that had cosine omega t plus theta, then I probably wouldn't start in that form, all right? So I want to start with whichever one is the most natural and then kind of go back and forth between them, okay? Problem 3, if you've gotten to that, problem 3 on the homework, that one started in what? I guess it started in complex form, right? And then you got to translate back and forth between the other two, all right? No.
You have multiple forms in the same one.
You could have multiple forms in the same one. All right. Well, maybe we'll talk. We'll go look at an example of what that might look like here. All right. So you could easily have multiple forms, which means that you're probably going to have to do a little bit of translation before you can start to do everything. The process we're about to do here. So all right. So last time we talked about this. So step 1, what's the fundamental period or frequency? How do I approach that part? how can I do that? I gave 2 ways of doing it last time. Right. The way that I would probably do it is not the way that I learned to do things in 5th grade math. Right. In 5th grade math, you learn things like least common multiple and greatest common factor and greatest common divisor. Okay. I don't remember that stuff. Right. I had to think about this myself before I even gave those problems. If you asked me, how would I find the fundamental period of this? I would graph it. And I'd look at it, and I would basically look to figure out what the largest period is that I can observe in that thing. All right, that's what I did, and I said, this is the way I would do that. So I have a video that shows basically how to get these data tips here. They're called. All right, so I basically looked at the peaks of the waveforms, and I said, well, this peak happens at an x coordinate, meaning a time value of negative 0.005004. This guy happens at negative 0.001004. So I took the delta between them, right? The time between them was 4 milliseconds. 1 over 4 milliseconds is 250 hertz, right? That's to me, that's the most obvious way. All right, because I'm more used to thinking of things from maybe an experimental approach. Right. The other thing I said you could do is this greatest common divisor approach. You could look at all of the frequencies that are present in the waveform and you could get the greatest common divisor. All right. Now, again, I hadn't thought about the greatest common divisor in many, many years. Right. So MATLAB has a function for doing it. Right. GCD. GCD. Now, what it's set up to do, and you may be able to find a more eloquent way to do this than I did it. But in this particular case, what I know is that MATLAB's GCD command takes the GCD of 2 numbers. So what I had it do here is I said greatest common divisor of 1750 and 1500, and then take the greatest common divisor of that result with 1000. Okay, and that will work. There may be a more eloquent way to get it to do it for 3 numbers, but I didn't pay enough attention or work hard enough to figure out how to do it, but I know this will work too. All right. Yeah. So, all right. So, greatest common divisor doesn't like.
It only answers for integers.
It only answers for integers.
It doesn't accept.
That may, okay. So yeah, the chatter here in the room for those of you guys online is basically if you go into MATLAB and use GCD, it doesn't like you giving it decimal numbers, which it probably doesn't because my son who's in 6th grade was learning greatest common stuff before he knew what a decimal number was probably. So yeah, it probably does make sense that that's the way it is. So if you were doing that, so like for instance, I'll talk about that real quick. So I think if you're talking, I didn't even bother thinking about that one because I can do it by inspection 4.3 and 12.9 and I kind of know what it should be. But if I had 4.3 as one frequency and 12.9 as the other frequency, it's not going to like that if they're decimals. But if you multiplied those by 10, right, they'll become non-decimals. You would, yeah, well, hopefully people can figure that out. All right. And there's probably all kinds of fanciness. You know, MATLAB can make you breakfast probably if you wanted to, right? I'm sure there's all sorts of toolboxes that you could probably pull up to do this. All right. That's why I guess I'm old school, right? I just think of it the way that I look at the waveform. All right, but the bottom line is once we got the frequency, this is the key thing, because when you look at this guy here, I don't even see 250 hertz as one of the options, right? And that becomes a little bit tricky. Now, what about the DC guy? Isn't he the fundamental? Yeah, trick question. It's the 0 frequency term. In other words, you know, the 0, this guy has a frequency of 0. So this is not the fundamental, right? The fundamental is the smallest frequency that's there. Technically, the smallest frequency that's here is 0, All right, but the smallest frequency that I see kind of repeating in the waveform is the 250, right? That's the part that we got to be careful of. Okay. All right. So the question, second step is, what harmonics do I have? Right? What harmonics are actually physically present in this particular case? So what we did last time is the same thing. I said, I'm going to do this way. I'm going to say N, F, and I'm going to talk about which ones I have. Okay. So N equals 0. What's the frequency? 0. N equal to 1 in this case. What's the frequency that I get? 250. Okay. So first of all, I guess what I'll do here is, do I have it? That's what I'll put in my third column here. So do I have a DC term, a zero frequency term? Yes.
Yes.
Okay. Yeah. Now, do I have a 250 term? No. All right. Now my second harmonic would be 500, right? 2 times that. Do I have that? No.
No.
All right. Third is 750. Do I have that? No. All right. Fourth is 1,000. Do I have 1,000?
Yes.
Yes. Now notice I'm doing this in terms of F, right? So I have 1,000 hertz. I got a kilohertz. All right. 5, 6, and 7. All right. 5 would be 1,250. 6 would be 1,500. And 7 would be 1,750. All right. So it looks like I don't have a 1,250, but I do have a 1,500 and I do have a 1,750. All right. So if you look at the way that I put this stuff into MATLAB, or the way that I asked you to put stuff into MATLAB, is I basically said N equals 7. I got 7 total harmonics to think about here. All right. 7 total harmonics. In theory, there's infinitely many, but there's basically from 0 up to 7 matter to me. Okay. So let's keep going with this. So step 3 is basically to figure out what coefficients we've got, right? So I put this table in here. And so the way I thought about this is I said, okay, well, we already said this. If I look at the signal 10 plus 50, whatever, right? If I look at that signal, I see that it fits nicely into that sine plus cosine form of the series, right? And if what I did here is I wrote out for, N equals 0 up to 7, okay? And then for all the frequencies, I wrote out the AN and the BN values simply by inspection. And there should not be, I don't know that I want to try this. No, it crashed my computer. But this guy should be 0. And this guy should be 0. All right. Let me go to full screen here. All right. All right, there we go. Come on. Wake up. Okay, there we go. All right. So what I see with this here is I did this by inspection. So I went through and I said, I have a cosine term. The first cosine term that I have in the series happens at the 4th harmonic, right? The 4th harmonic was 1,000 hertz, right? That's this guy right here. So I put a 50 for the AN value there at the 4th harmonic. Now, the next two that I had, so I had a 2 sine 2 pi 1,500. That 1,500 we said was the 6th harmonic. So I put a 2 there in the B sub n column. All right. And then my 7th harmonic was 1,750. So I put a 20 in that column. All right. Now, what about the DC term? All right. The thing is goofy about the DC term is it says the DC term is A0 over 2. and I see that A0 over 2 has to be equal to 10. Again, I just pattern matched there. So A0 over 2 is 10. So that means that A sub 0 is 20. Okay, you just got to be careful about that. All right, but again, I'm just, I mean, that's not my definition. That's, you know, Fourier's definition. So I'm just going with the way it's defined. All right, that's my first step. I like to think of it in that kind of table like that. Now, if you look at the way that I ask you to do that in MATLAB, let's say, right, in your solution, I got to enter something that looks like this: A sub n equals, and then I put 2 row vectors in there like that. All right, that's the way that I tell you to do it in the homework. So if you look at it, I got A sub n, and I tried to line these guys up on top of each other in the way I put this here so I can follow it logically, right? So if you look at this, so n equals 0 is everything in this column right here. N equals 1 is everything in this column. N equals 2 is everything in this column. N equals 3 is everything in this column. 4, 5, 6, 7. Okay. So what I did was I basically translated what I had over here in the table. All right. I translated the table over into these row vectors over here. Okay. All right. That's as simple as it gets for this. Now the question would be, all right, so that gets you for one part of the problem, right? I know what my A sub n and my B sub n are. How do I get to my other forms of the series, right? So there were other forms we said, right? Let's say I've got it now. I've got the sine cosine version done, all right? Now I want to go to the shifted cosine version, the middle one there. Well, what do I do? Well, we derived what the relationships were between, let's say, if I had A cosine omega t plus B sine omega t. By trig identity, you can relate that to C cosine omega t plus theta. Okay, we did that. We talked about that. We're not big on deriving stuff. So what I want to do is I just want to use those results. We talked about this before, all right, and use these results. Technically, if I have a cosine or a sine at any given frequency, again, to me, if in circuit analysis, this is the way we think about things. I have a cosine with a shift and a scaling, okay? And I can think of that thing with a shift and a scaling as the sum of one cosine plus one sine at the same frequency. I can think of it as 2 vectors, one rotating one way, one rotating the other way. Or I can think of it as the real part of this whole thing. All right? 4 different ways of thinking of it. And if I remember those relationships, I can easily get back and forth between the different forms. All right, so here's what I've got here is I've written out the forms, and this is the way that I think about it, is I look at this table. All right, I look at this table here. All right, so if I start with the shifted cosine version, here's the result of the analysis that I've done previously. All right, is C cosine omega t plus theta is the real part of this whole thing. So if I did the math out, then I basically got this. And the A and the B terms in this equation, the A and the B terms in this equation are what's shown right here. A equals C times cosine theta, B equals C times sine theta. And I could represent those in vector form like this, A plus JB, okay? And the other thing that I derived previously is if I use Euler's identity, so to do this, I basically said, if I had C cosine omega t plus theta, I could use Euler's identity to say that that's C over 2 times e to the j omega t plus phi, or theta in this case, plus C over 2 e to the minus j omega t plus theta, okay? And you can factor that into the form that I've written here, okay? So what I do in this case, it looks like what I have is if I have a single cosine at a single frequency, that means that I have an e to the j omega t at a positive frequency and an e to the j omega t at a negative frequency, right? Everything in the complex form of the series that I have at a positive frequency, I have to have at the same negative frequency because I need those 2 vectors, right, that are rotating in opposite directions to cancel each other. So I'm going to have one at a positive frequency, one at a negative frequency. All right, we're going to use that a lot. All right, and so what I have is is what's written here. So notice this guy has two coefficients. It's got an alpha 1 and an alpha minus 1. All right. And here's the relationship. So basically, I can relate all of those coefficients with the equations I have here. Okay. All of these guys with the coefficients I have here. So let's use those relationships to figure out how we get back and forth between the different forms of the series. So where did we start? We got our AN and BN. Right? We started with essentially the sine cosine form of the series. All right. So where's the easiest place to go first? Well, I'm going to go to the shifted cosine version. All right. And so I go to this table. This table right here is my pathway through all of these problems. I look at this. Again, there's a lot fewer equations on this slide, but this slide has all the equations you need. There's a lot fewer than what's in section 9.1 of the book. Right? There's like 50 equations in that section. All right. If I look at this, and again, I got this through trig identity. Basically, A is equal to C cosine theta, and B is equal to C sine theta. All right. So I can relate from the sine cosine version to the shifted cosine version simply using those formulas, right? So basically what I do is I start in the middle here. And I say, well, that I can think of the C as a vector, right? Right. So I can think of C as the magnitude of the vector A minus JB. Okay. And then the angle of that vector is going to be what I get for this. Okay. The angle of that vector is going to be what I get for this. So to code that, what I did basically was I said this. I said, I took the magnitude of the vector, right? So in other words, you look, right? You're given the A and the B values, right? You're given the A and the B values. So if I look at the A and the B values, if you look at this, remember your C values have to be, so your C values would have to be C equals the square root of A squared plus B squared, right? And your angle values would relate to the fact that this guy is a vector with some angle, right? It's got a real part with a cosine and an imaginary part with a sine. So I related those like that. All right, notice what I did. I said my C sub n is the square root of AN squared plus BN squared. Now, why did I do the dot squared here? It squares the individual elements. It's an element by element operation. I wanted to square each of these elements here. So I wanted basically 20 squared, 0 squared, 0 squared, 0 squared, 50 squared, 0 squared, 0 squared, 0 squared. All right, and I wanted that added to the square of every element in B sub n. All right. Theta n, I basically said, okay, well, give me the angle of this vector here. All right, and because I like degrees, I multiplied by 180 over pi. Right, you could do radians to degrees if you wanted to do it that way. Okay. Now, I've gotten myself to the shifted cosine version of the series at this point. Okay. Now I need to get to the complex version. So what I do is I say, well, I just think of it, how do I shift back and forth between these different forms of the series? So for me, what I'm going to do is I'm going to try to relate the shifted cosine version over to the complex version. All right. And that's pretty simple for me to do because once I have A and B, right? Once I have A and B, I can easily relate these two guys via the relationships that I have here. Alpha 1 is that vector divided by 2. All right. And again, that comes from Euler's identity. And alpha minus 1 would be the same thing except what? What's the only difference for alpha minus 1? What would alpha minus 1 look like?
It's C over 2 e to the negative j theta.
Yep, C over 2 e to the negative j theta. Okay, e to the negative j theta. What do I call C over 2 e to the negative j theta? What's its relationship to A1 or alpha 1? Sorry. It's the conjugate.
Is it the imaginary part of
Complex conjugate.
Yeah.
Right? The complex conjugate. Right? So now that I know C e to the j theta, I can very easily get to my alphas. All right. So once I have one of them, I can easily relate them back and forth via all the equations that are on that slide. All right. So if I go back here to the series itself, okay, different forms of the series. One thing I want to note here very carefully is if you look at the sine cosine version, right? You look at the sine cosine version of the series and the shifted cosine and the complex form. What's different about the complex form relative to the other two?
Exponential.
Well, it's exponential.
Is it alpha?
It doesn't have the DC term floating on it. Key thing is look at the terms on the summation there.
Ends at negative infinity.
It goes from negative infinity to infinity. Because if I use the exponential, two complex exponentials will always equal a cosine. But I have to have one that's in the forward direction, so a positive frequency, and one that's in the negative direction, so a negative frequency. So there always has to be two, okay? So let me ask you this. So when you go into MATLAB to code your stuff, I have harmonics that go from, we just said, from 0 to 7, all right? But when I do this with the complex form of the series, I'm gonna have to go from what to what? Not from 0 to 7, but from where am I gonna start in the complex form of the series? Negative 7, yeah, negative 7 to 7, all right? Negative 7 to 7, which makes it uglier, there is no doubt, all right? So there's some elegant ways to do that, but it's definitely a little bit uglier, all right? So if you look at the way that I coded this here, so let's think about this for a second. It's pretty easy to do the positive ones, right? If I've already figured out C and theta, it's super easy for me to do that, right? How could I write a piece of code that would do that for me? If I know C and theta, so in other words, I have what I have here. How could I write code that will give me the positive, so alpha 1, when I say the positive ones, I want to get alpha 1, alpha 2, alpha 3, alpha 4, alpha 5, alpha 6, alpha 7.
You can do a full loop.
I could do it even simpler than that. For loop's actually the best way to do it. All right. And that's actually a good answer. But essentially for any given one of them, right? What I could say is it would be C of 1 divided by 2 times e to the j theta 1, right? And I could do the same thing for alpha 2. It would be C2 over 2 e to the j theta 2. And I could just code that in there, all right? And a for loop would be a really elegant way to do that. All right, when I say it's elegant, well, it's because I get something like this. Here's what I did, and I wanted to talk about this here for a second. So what I did was I created this guy as alpha positive and alpha negative, okay? So alpha positive here started at 1 and went to 7, right? We said that's how many harmonics I got here. I got 7 harmonics. And so what I did was I entered the coefficients by hand, right? So I put 1, 2, and 3 were all 0 because I didn't have a fundamental, a second harmonic, or a third harmonic. The first one I had was a fourth harmonic here, right? A fourth harmonic. And what I did was I put in, again, I did it by hand here, all right? I said 50 over 2 times e to the j theta n at that entry times pi over 180. Now I did it pi over 180 because I had saved everything in degrees, all right? You notice I always save everything in degrees because when I want to think about whether my answer is correct, I can think more easily in terms of degrees than I can in radians, all right? Now, what I did next is I put alpha 0 by itself. What is alpha 0? What frequency does alpha 0 correspond to here?
The DC.
The DC term, all right? Alpha 0, if I look at it, go back to the form of this series, if you plug in n equal to 0, alpha 0 is just the DC term. All right. And so when I look at the equation, the DC term is 10. And so I put in alpha 0, go back to it here. I put in alpha 0 equals 10. And then to make alpha negative, now I could have gone in and I could have written each one individually, right? But that would have been like 15 things to enter by hand. I didn't want to do that. All right. So what I did was I did this guy here. I used the command I've never talked about here right there, flip LR. What do you think that does? Flips the vector left to right. So it takes the last entry and makes it first, makes the first entry and makes it last. All right. So, and what's the conj command do? Takes the conjugate, right? Because I said that for when n is less than 0, it's the conjugate, right? So I basically forced MATLAB to do the work for me. All right, and then what am I doing in this last step here?
You're putting in the vector.
I'm basically concatenating those different little subvectors together. I'm saying I want a vector. That's what the square brackets there say. Make me a vector with the vectors that I'm putting into that vector. So it starts with alpha negative, right? And I want to start with alpha negative because that's negative, right? Those are the negative components. Then I put alpha underscore 0 in the middle, and then I go all the way up to alpha positive, right? So I include all of those there, okay? The more elegant way to do it is what I've got here. All right. So what I did was I basically, so let's talk through my code a little bit here. All right. What I did was I said, let's make my n vector. It goes from 0 to 1 to 7. And you don't have to do what I'm doing here, right? You could manually go through and you could put in all 15 values in the vector by hand. Nothing wrong with that, right? It's a lot easier to do what I'm doing here if you're more comfortable with it. Right, but I know that not everybody's comfortable enough with the code to write a for loop like I have here. Right, what I did was I said, okay, we'll make a vector n, which with all my harmonic numbers. N goes from 0 to 7 in steps of 1. And then I created these two empty vectors, alpha positive and alpha negative. Okay, they're empty. I said they're equal to empty vectors. That's what the empty square brackets mean. And then I say, I have a for loop that says, let's go from 1 in steps of 1 up to length of n. Okay, so n was my harmonic number. So I'm going to go from, basically, I'm going to run the whole length of the n vector. And then I got some if statements here. All right, my if statement says if n of k equals 0, then do this. Otherwise, do this. So let's think about what I'm doing here. I say, what I got here is I say alpha underscore positive equals this whole thing. And then alpha underscore negative equals this whole thing. So notice what I'm doing here. Alpha positive equals alpha positive. And then I have this statement. So let's first just unpack this statement right here. Right there. Let's just unpack that statement. What is that statement doing? What have I written there?
The formula from the previous page.
This is my alpha n right there. Okay, that's my alpha n. I've just put the formula in there. Now, the fact that I say alpha positive followed by that, what am I doing? I'm concatenating another value on at the end, right? And so by the time I'm done, I should have 7 values that have been written in there. For alpha negative, I'm doing the same thing, right? For alpha negative, this guy here is alpha minus n. But that's going to end up in the wrong order, right? If you think about this, I'm going to put the -1 term first, then the -2 term, then the -3 term, then the -4 term. All right. And so what I do at the end is I do a flip left right, right? When I concatenate everything in that last line. Yeah, Philip.
Instead of doing the flip left right, could you just put the alpha negative after the a negative n?
Yeah, so there's, with code, there's 1,000 ways to skin a cat. Yeah. Yeah. There would be, yeah, I think you could, so Philip's suggesting another way that you could do this, which would be to put, I don't want to say it just yet because I might say it very ineloquently, but there's other ways that you could do this. All right. I like the flip left right approach. All right. Just flips the numbers around. Now, this whole thing, when I say if n of k equals 0, what's that if statement doing for me? What's that if statement got? If n of k equals 0, what is that? What's happening at n of k equals 0?
It's for you to take care of that DC.
Yeah, it's for the DC part. And I know that the DC part, right? So the DC part, if I looked at the series, it's C0 over 2 and A0 over 2, right? But it's also alpha 0. So at the DC parts, this is the relationship between the DC parts. So what I did was I said for alpha 0, it's just that. It's half of whatever C of 0 is. Okay. Now, that's a more elegant approach, but you totally could just write a vector in your MATLAB code that says alpha equals, and you could manually enter in every one of them. Perfectly fine if you're not comfortable with this, but this is a little bit more elegant. And you could probably become even more elegant still, right, than what I'm doing if you really wanted to. All right, but this would work too. All right, now, question would become, how do I graph that stuff? All right, let's say I wanted to draw a graph of it. So let's say I wanted to create the graph that I showed at the very beginning. I wanted to draw that graph. Right? I should be able to because I've got the coefficients now. So what would be a way that you could write code to do this? Again, there's some brute force ways to do it, which would be, you know, for instance, in problem 3, I ask you to draw a graph. Totally do it by just writing out every term in this series. Nothing wrong with that. You can totally do it. There's only 5 terms, so it's not hard. But I could do what else? The fact that I have these summations.
You could just loop it.
I could loop it, right? I could loop across the harmonics. And so I'd get code that might look something like this, okay? So what I have here is I got a for loop, and I'm going to create, so I see, what I have here is x underscore 1, x underscore 2, x underscore 3. And I created basically 0 vectors that have the same size as my time vector. So somewhere else in my code, I defined my time vector, okay? And then I loop from 1 to 1 to length of n. And I guess I included n above, but n is basically a vector in this case that's going from 0 to, in steps of 1, up to 7, okay? And what I did here is I've got my if statement again. All right. I'm going to jump down to the else here first. My if statement says if n of k equals 0. So if n of k equals 0, what does that mean again? What condition is that when n of k equals 0? That's my DC term. All right. So for any other frequency, let's go to the any other frequency first. That's where I go to the else. Right. What I have in my x1 is I am implementing that summation, right? So what I'm doing is I'm saying take the vector x1 and add to it. So this is what I have right now when I come into this loop, and then I add to it this statement. C of n k times blah, blah, blah. So basically I'm implementing this guy right here, right? And if I run through this loop 7 times, every time I run through this loop, I'm going to add another harmonic into it, okay? Then my x of 2, I do the same thing. If you look at it, I just keep adding to the summation. In this case, I took my an values and I took my bn values, okay? Now, if I look at the DC terms there, what did I do? What did I do different? Well, I added to what I already have because it's a summation, right? But what did I add here? What's different about this? About these statements?
The one size t. You can
Yeah, so what does one size t do? What does that do?
put in the size of your t vector, but you're
Yeah.
from some ones.
It does. It basically creates a vector of 1s that's the same size as my t vector, and then I multiply it by a number. Cn of k over 2 is a number, right? So I basically throw that number in there, and I get a graph. All right. Now, ultimately, my graph looks like this, like it should. All right. But here's the complex one. All right. Complex one's a little bit trickier because I also have to add in the negative terms. All right. So if you look at what I did was I defined a vector n complex that goes from -7 to 7, steps of 1. And then I loop over the length of that vector in increments of 1. And I say, well, when n complex is equal to 0, what is that if statement? If n complex is equal to 0, where am I in the series? What frequency am I at? 0. I'm at my DC term. Okay. And so what I do there is I say, well, add whatever my x3 is, because that's the vector I'm storing the complex form in. Add to that alpha n to whatever alpha I have there times 1s, right? I'm adding the DC term in. Everywhere else, what do? Well, I add in what it says right here, right? I add in this. I say alpha n times exponential j times n times omega times t. All right, and if I do that, and I plotted all three of them on top of each other, this is a good check to make sure you've done everything right. If all three of them sit on top of each other, then good, it works. I've done it right. All right. So what I've plotted is I've plotted all three forms of the series, right? I plotted x1, x2, and x3, and I defined them here. So x1 was the shifted cosine form of the series. x2 is the sine cosine. x3 is the complex form of the series. So I did all three of them sitting on top of each other, like that. All right. And they should, if they don't sit on top of each other, but in other words, when I say sit on top of each other, in other words, I see one graph there. If they were not sitting on top of each other, you'd see three graphs on there, right? And so when they're sitting on top of each other, I know that I did everything right. If they don't, you did something wrong. If they do and it's not taking your answer, then I did something wrong. All right. All right. They should, I mean, unless somehow you did the wrong answer in a really elegant way, right? But most likely, if all of your graphs sit on top of each other, then I did something wrong in my setup of the problem. Okay. There's the code.
Did you just grab the one first?
You don't believe me. You don't believe me.
I mean,
I have this, I'll post these notes, right? I'll post the code too, so you can turn them off if you want to see it, right? My computer doesn't like closing the PowerPoint, opening the PowerPoint again. So but try it out. Now, the thing I do want to say is x of 3 here is you're adding complex terms, right? Which MATLAB will typically give you that warning. You've probably seen this warning. I can't plot imaginary parts, right? Well, what's going on? It's not supposed to be imaginary, right? x3 is not supposed to be imaginary. I thought it was all real, right? Wasn't it supposed to be entirely real when I added that stuff? So why would I get that warning from MATLAB? He's basically, oh, imaginary parts. There's imaginary parts in a vector. If you get that warning, it means there's imaginary parts in a vector that it's trying to plot. It's a rounding error. All right. So what I did was I said, all right, just to assure you of that, to see what I mean, because this is kind of important, right? In figure 2, I plotted the imaginary parts of x3. So there's some there. It's times 10 to the negative 15, right? 10 to the negative 15 is 0. All right, that's, I don't even know, femto. Is it femto or is that, yeah, femto, yeah, femto volts. All right, that's pretty small. All right, so there's basically some numeric errors because it's a computer and it has finite precision, right? It can't represent numbers with infinite precision, right? And so there's some errors when it does its math. But effectively, the imaginary part is gone. All right, if I plotted this on the same scale as this, it would look like 0. Okay. All right, so that leaves us, so this should help a little bit. Now, maybe I'll try real quick. I'll talk more about next time. Okay, well, let's say I had a more general problem and I wanted to figure out so I don't have an equation for that guy, that ugly looking waveform there. I don't have an equation. How do I figure out the A and the B and the C and the alpha? Well, there's an approach to it, which basically involves that picture that I have right here. All right, so I want to think about the equation picture-wise, because as an engineer, I could build that circuit or I could build the code that'll do this. And so I like to think of it in terms of that kind of an engineering picture as opposed to just an equation. All right, because this is how a real system works. If you use a device called a spectrum analyzer, this is what a spectrum analyzer does, is it basically does this computation that I've shown here. But I'll try real quick to maybe just address the question that I think you had. There was a question that said, what if I had, I don't know, 3 cosine t plus 4 cosine 2t minus 30 degrees. Let's say I had that. Right? What should I do to start getting that into some form? Well, you could start that in the C form if you wanted to, yeah, and you could say, okay, this guy must be, right, you know, C of n as a vector. It's got no DC term. It has a 3 for the fundamental, and it has a 4 for that guy. And then my theta n would be, there's no theta to my DC term, right? There's no theta to the fundamental, and there's a negative 30 to that. And then I can start relating that to the other forms of the series using those equations that I've got there. Okay. All right. You guys follow that? All right. So it's, yeah, I think this will help. I'll post the video and this, and I think it'll help a little bit. And the code here is very similar to what you would have to do to think about making that graph. Again, there's easier ways to make that graph, right, in problem 3. But this approach, you're going to be using this approach in the next homework and the homework after that, right? So it wouldn't be a bad thing to get comfortable with it now. All right, so I'm going to stop there. Stop the